Before I give my presentation, I want to introduce a little person named Rar. He is a tiger, and he travels with me all over the world. Whenever I give presentations, he helps me present, and I usually take pictures and send them back to my son, who follows along, and this is how my son and I communicate while I'm traveling. My son is now 9 years old, so I think he's getting to that age where this is no longer going to be cool for him. So I'm enjoying this last year probably. So Rar will sit here while I present. So thank you so much again. It's an honor to be here. It's an honor to be invited to speak at your conference. This is a great conference. Lots of people. You're probably one of the largest crowds I've spoken before at a PHP conference. So thank you very much. One of the things I like to do before my presentation is to go ahead and put the slides online. I've already done that. This way, if you want to download the slides or view them from your laptop or phone locally, you're able to do that. A little bit about me. My name is Ben. I'm a web developer. I am a speaker. I'm an author. I help and work at a place called Shootproof, where I build a platform for professional photographers to help them sell their pictures directly to their clients. I work remotely from Nashville, Tennessee, as I said earlier. Now, I've been around the PHP community for many years. As I was telling someone earlier, this is probably my 11th year giving presentations, and this is my 106th talk, I believe. I'm a co-author along with Davey Shafik of the Zen PHP Certification Study Guide. It's now out in its 3rd edition, and you can get this at phparc.com through PHP Architect magazine. I'm sorry if I mention them if they're a competitor with iMasters. But this is a good resource, even if you don't plan on taking the Zen certification exam. I founded the Atlanta PHP User Group in 2004, and I'm currently a co-organizer at the Nashville PHP User Group. And I've heard about the Sao Paulo PHP User Group for many years, and so and I've always been very impressed with what you're doing down here. I contributed Array Column to the PHP core. I currently maintain a UUID library, which is now out at 3.3.0 and 2.9.0 as of today, which fixes a UUID collision problem. So if you're using that library, it's time to upgrade. And I am the maintainer for the League OAuth 2 client through the PHP League of Extraordinary Packages. And don't blame me for the name, the League of Extraordinary Packages. First, a little disclaimer about this talk. HTTP is dead. Long live HTTP2. Sort of a play on the king is dead, long live the king. Even though the talk is about HTTP2, I cover HTTP1 because HTTP1 is just as important today as it ever was, as you'll find out in a few minutes. But before I get into all of that, let's take a look at a little bit of web history. In 1991, Tim Berners-Lee at CERN in Switzerland creates the first World Wide Web server. And it serves the first HTML pages. The version of HTTP he uses comes to be known as 0.9, and it was a subset of the 1.0 draft he was working on. It was very simple. At this point, it only supported the GET method. Then HTTP 1.0 continues in draft form over the next few years, heavily influenced by a guy named Roy Fielding. You might know that name from REST, or Representational State Transfer. And the IETF HTML working group continued, or HTTP working group continued to drive the progress of the draft. Then in 1996, HTTP 1.0 comes out as RFC 1946. This version expanded the methods and the headers, but did not support the host header, which is really important to HTTP today. Because if you don't support the host header, then the web server doesn't know which site to serve. So as a result, you can only have one website per IP address. But then in 1997, HTTP 1.1 was published as RFC 2068. There were many new headers added and a few more methods. This is the version that we've used for so many years. But as you'll see in a minute, this wasn't the end of version 1.1. In 1999, HTTP 1.1 was revised and clarified, and several headers and methods that weren't being widely implemented were removed, such as patch, link, and unlink. And as you might know or be aware of, these methods have been added in later RFCs. This is the version of HTTP that stood frozen like Han Solo and Carbonite for so many years, for over 15 years. Not a lot changed, although there were a few little things that happened along the way in terms of progress. And I've got a few of those up here. But then in 2007, the IETF formed the HTTP working group. A few more things that happened along the way. A few more RFCs that kind of updated HTTP came out. And then a big major thing happened in 2014. This is when this working group, the HTTP working group, revised and clarified RFC 2616, creating 6 new RFCs, 7230 through 7235. I'll come back to these in just a moment. And then in May 2015, a big announcement was made when HTTP2 was ratified and finalized as RFC 7540. So when I say HTTP is dead, HTTP itself isn't dead, but RFC 2616 is dead. We no longer use this version number when talking about HTTP 1.1 anymore. In fact, we have 6 new RFCs. There were some reasons for this. It was old. It had not changed at all since June of 1999. It was 176 pages. Now, if you've ever looked at any other RFCs that have been published, most of them are no longer than 10 or 20 pages. This thing was a beast. It was giant. And as a result, it was very complex and very complicated and hard to understand in a lot of places. Because of that, there were a lot of errors and there was a lot of ambiguity in the RFC. And so not HTTP2, these new RFCs, these 6 new RFCs, sought to fix this. Finally, and this is the big thing, the web got much bigger than anticipated. You can imagine in 1996, 1997, 1999, when these RFCs were first published, no one imagined that we would be using HTTP as our main transport across the internet. But it's become our main transport for APIs and for all kinds of services. And so they needed to revise and clarify HTTP 1.1 in order to suit the new web. And the group that did this was called HTTP BIS. Now, I am told that in Portuguese, this is very easy to understand because BIS is a word in Portuguese. But in English, this is not so easy to understand because we don't have an adverb for the word to. So I think everyone here will understand that this is the second HTTP working group. It was chartered in October 2007 to refine and clarify HTTP. Now here, they are specifically forbidden from creating a new version of HTTP. In fact, their charter says the working group must not introduce a new version of HTTP, and it shouldn't even add any functionality to HTTP. They should not produce new methods, new headers, or extension mechanisms. They're just there to revise and clarify. And what do I mean by that? Well, remember when HTTP 1.1 got revised and clarified in 1999? And they removed methods that weren't widely implemented? Well, that's what their task was here. They were supposed to take a look at how the web was being used in 2007 and revise and clarify HTTP 1.1 to update it for how the web is being used, for how HTTP was being implemented. And this resulted in 6 RFCs. The first one is message syntax and routing. So as I said earlier, HTTP 1.1, or RFC 2616, was 176 pages when printed. This split them all out into individual RFCs. The message syntax and routing is one that we don't really pay attention to a lot, but we use all the time. And that's because this defines how HTTP is transferred over TCP. Then 7231, this is the one that we all look at a lot in our applications. When you're developing an API or working with an API or even just building web browser pages, the semantics and content RFC is the one that most affects your daily work. This is the one where all of the methods and headers like get, post, put, and delete are defined. And this is the one that sets up some new registries to make HTTP more extensible. I'll talk a little bit more about that at the end of this slide. The second one is conditional requests. Then they just go into more detail. So they split out the conditional requests. They split out the range requests, the caching, and the authentication all into their own RFCs. And what they did in each of these is they introduced registries to allow HTTP to be extended even further. And so if you go look at these, you can take a look at a registry of all of the headers and all of the methods and all of the cache conditionals, all of the range types that you can use, all of the authentication mechanisms. And so now new RFCs can be created to extend HTTP without having to override or get rid of these RFCs. So RFC 7230 something is the new 2616. So keep that in mind, etch that into your mind, and get rid of this notion of 2616. It's gone. It's dead. Now let's talk a little bit more about HTTP BIS. They've worked to refine and clarify HTTP. They've migrated it from one monolithic specification, one ginormous thing, into 6 sizable specifications. And they've paved the way for managing new extensions easily through these registries. Now remember back to 2007? The working group must not introduce a new version of HTTP. They were forbidden from it, in fact. Well, some things changed along the way, and you might remember these. In 2009, Google announces their Speedy Protocol project, which is designed to increase the speed of the web. There's some interesting things about this. They wanted it to be an open protocol. They wanted the community to be involved in helping design and steer it. But it was still helmed by Google. Now, the next year, Google releases Speedy support in Chrome for all versions of Chrome 6. This is important for them because at this point in time, Chrome was gaining adoption. In fact, I think it had become the predominant browser on the web. As a result, Google could effectively use their new protocol in order to speed up the web for their properties because they could build it into Chrome, their client. And in 2011, Google deploys Speedy across all of their Google services. At this point, we're starting to see real-world effects of the Speedy protocol. We're starting to see real results. So in 2012, some other major things happen. As a result of seeing the real-world results that Google had presented from what they had seen, Twitter decides to adopt it. Facebook adopted it. WordPress.com announced support for it. All of these brands started to see, hey, Chrome has support for Speedy. A lot of people are using Chrome. We can take advantage of this. Then the IETF amends the HTTP BIS charter, saying, There's an emerging implementation experience and interest in a protocol that retains the semantics of HTTP. That means it retains the headers and the methods and all of that protocol we're familiar with without the legacy of the messaging framework and syntax. That's that new 7230 RFC. The working group will leverage this to create a new major version of HTTP. And the very first draft of HTTP2 was essentially the current, at the time, speedy draft with some search and replace to change speedy to HTTP2. I'm not even joking about that. That's what they did. So that helped, got rid of that whole Google at the helm. Some people were a little afraid of that. And that helped open it up to a broader community who could then participate and offer feedback and contributions to the draft. So in May of last year, about a year ago, RFC 7540 was published defining HTTP2. So let's talk a little bit about some of the reasons why we needed an HTTP2. I mean, after all, speedy sounds great for something like Google, who has these huge properties that have all these servers. Maybe great for Facebook and Twitter, but why is HTTP2 relevant to us? Well, there are some problems that we face as web developers. And the HTTP BIS working group saw, as they saw an increased interest in speedy and proven results from Google using it, they realized that a better TCP binding could help improve everyone's experience on the web, while still retaining all of the headers and methods that we're familiar with. Here's some reasons for that. HTTP 1.1 makes inadequate use of TCP. It's ASCII over TCP. It's plain text. That's not very efficient. And even when using TLS, which compresses that's the secure sockets layer, when TLS compresses it, the packets could really stand to be sent in a more efficient manner. Now, TCP is a good protocol, and it's not going away anytime soon. In fact, it's being used even more. While some people are using UDP for gaming and stuff like that, TCP is important for sequential communication. Another reason that HTTP2 was important is that the transfer sizes and number of objects that we send across the wire these days is exponentially increasing. In fact, in this graph here that Daniel Stenberg has in his book, HTTP2 Explained, he noticed that since 2011, the number of objects has risen from 80 to over 100. And when I say objects, I mean when you make a request for a page, all of the objects on that page are the images and JavaScript files and CSS files that it also must load in order to render the page. So he noticed that object size was increasing. It's only going to continue to increase as we build richer web applications. And the size of all of those objects together has risen from over 800K to over 2.1 megabytes. Now think about that. Like, when in the early days of the web, we tried to make pages have as small a footprint as possible. Now we don't. Now, because people have better bandwidth, we just go ahead and send them the large files because it gives them a better experience. But the problem is that we have latency issues. Even though bandwidth has increased, the server response time has not really increased much. And that's because of this protocol that we've been using. The server round trip has not greatly improved. And while HTTP pipelining exists, most have turned it off because HTTP pipelining has its own problems. In Daniel Stenberg's book, HTTP2 Explained, he describes HTTP pipelining like waiting in line at a bank or a supermarket. You don't know if the person in front of you is a quick customer or that annoying one that will take forever until they're done. And this is called head-of-line blocking. Now, I have a short video here by Ferdinand Lutz called stay in queue that I think illustrates head-of-line blocking perfectly. Now, there's no great solution for this. And today, most HTTP browsers have this feature turned off because you can't really know how fast the line is going to be, and you can't really start up a new line, or you could, but the overhead to create a new stream is high. And in the case of HTTP pipelining, you can't even change lanes like you possibly could in the line at the supermarket. So as web developers, we've learned to deal with these issues, and we've written at length books and blog posts and articles. We've given talks, we've created training courses, and so much more. We've built an entire industry around solving these problems because we need to deliver web pages fast. So here's some ways we've done that. The first is through CSS sprites, or spriting. Because it's really better to send one giant image over HTTP than hundreds of smaller ones. It doesn't even matter if you need to only use one of those images. And if you need to replace one of them, well, good luck. You now have to bust the cache in order to replace it, because every web browser has downloaded this one big image. Another thing is inlining. We've taken images or SVG files or even CSS, and we inline it within HTML. The reason for this, again, is to reduce the number of requests you make to the server. Concatenation and minification. We take all of our JavaScript files and combine them into one. We take all of our CSS files, we combine them into one, and then we remove all of the excess white space. We've created tools and workflows all around these things. And again, sometimes we deliver these files and we only really need one or two of the functions or classes that they define. But it is still better for us to deliver them all as one request than to make a whole bunch of requests for each individual JavaScript class file or JavaScript function file. Another thing, and this is kind of wrapping all of these together, the theme here is reducing the number of requests. And the last thing is domain sharding. We still have to make a lot of requests. We still have a lot of images. And domain sharding is one thing we've come up with to get around the browser limitation of opening connections to the server. Browsers, at most, I think, will only allow you to connect up to make 6 connections to the same domain. That slows down the page load. Your connections might be fast, but if you can only have 6 open at a time, you're only downloading 6 things at a time. So in order to get around this, we use a bunch of different domains to serve all of our images from. HTTP2 attempts to fix these problems. Here's how it does it. The first thing is that it is a binary protocol. Now, at first, this may sound like a bad idea, something that would get you upset as a web developer. I know in my early days of web development, I used to pull up Telnet and just type the HTTP commands raw and then see the response. We won't be able to do that with a binary protocol, but there are a lot of advantages to having the binary protocol. The first one, the big advantage is the binary frames. When we're not using plain text, when we're using binary instead, we're able to parse the response faster and quicker because we can find the location of the frames. Each frame has similar properties. It has type and length, there's flags, there's a stream identifier, and a payload. Now there are 10 different frames specified, but the ones that are really important to us are the data and headers frames. So headers can be sent in a separate frame. Data, which is the body of your page, will also be sent in a separate frame. This is how they're organized. Each frame has a 9-octet header with information like the type, length, flags, stream identifier. The type would be things like data and headers. And there's a lot of other types of frames. One we'll look at in a minute is the push promise frame. And the beauty of HTTP2 is that a single connection, you only need a single connection. Earlier I mentioned that browsers will let you open at most 6 connections to the same domain. With HTTP2, you only need that single connection. It will use that single connection for all of its communication with the server. And in that single connection, you can have multiple concurrently open streams, with either endpoint weaving together frames for multiple streams. Now, oftentimes the order of frames that are sent matters, and recipients will process them in order that they are received. This is why the TCP protocol is important. But when you multiplex the streams, that means that packages from multiple streams can be sent mixed together, and they'll be reassembled together in the correct order on the receiving side. This puts an end to the head-of-line blocking we saw earlier, because they don't have to wait on the first person or the first stream to finish. It can go ahead and send the frames before that stream is finished being received. Here's how it works. This example, again, is taken from Daniel Stenberg's book, HTTP2 Explained, which I highly recommend. It's a free download. If you think about each stream or each set of frames as trains, and these trains have, each of their little byte order within the frame. When you send these across the multiplex stream, you can take those trains apart, take each of their pieces apart, put them together in a different order. They can be woven together, and then when the client receives them or when the server receives them, it knows based on the stream identifier which stream each one belongs to, so it can reassemble them into the correct streams. This, again, allows us to make faster connections and faster requests. Another thing that's cool is that streams can have priorities and dependencies set on them. For example, the client can use this to specify which streams are more important than others, and can tell the server that one stream is dependent on another. This allows browsers to do some pretty cool things. For example, when you're scrolling down a page, if there are images at the top of the page, the browser can separate those from the images that it knows are lower on the page and assign a higher priority to them so that they load faster. Or when you switch tabs, the browser can intelligently say, oh, the user just switched tabs. I'm going to make the streams on this other tab have a higher priority. Header compression. Headers can take up an awful lot of space in HTTP 1.1. And as I mentioned earlier, in HTTP 2, headers are sent in their own frame. As a result, we don't have to send them on every single request, especially for headers that duplicate effort. And lastly, server push is a feature that allows the server to send resources to the client before they're requested. Now this helps on the server side. The server could determine that for a certain page load, that it knows the client is going to request these images, or these style sheets, or these JavaScripts. It can go ahead and tell the server to send these along with this response so that they're already on the client when the client needs them. Great, but how does that affect me? Well, for the most part, this is seamless for web developers. But it will affect us in a lot of ways. One is that we no longer have to do image sprites. Inlining images will be a thing of the past. CSS and JS can be in multiple files, and domain sharding is unnecessary because we only need a single connection. In fact, these kinds of things could hurt us if we do these, if we continue to do them, especially the domain sharding, because now you have multiple domains, it has to open different connections for those instead of reusing the same connection. Awesome. I'm going to go do all of that right now. Well, not so fast. We're still in an HTTP 1 world. Now, I first gave this presentation in May of last year. At that time, this was 100% true. But big players like Google, Twitter, Facebook, and so forth now have rolled out support for HTTP2 across the board, and Firefox and Chrome fully support it. So folks are catching up. As of right now, 6.8% of the top 10 million websites support HTTP2. And a lot of the browsers are catching up. So IE has some support, but Edge, which is Microsoft's bleeding edge browser, has full support, which means that IE will probably have full support soon. Chrome, Firefox, Opera, iOS on Safari, Chrome for Android all have full support. Safari on the desktop, not quite full support, but it's getting there. And the other thing that's important are web servers. You can't really do HTTP2 without a web server. So Apache now has support in mod HTTP2. Nginx now has support. IIS 10 includes support. So what can I do now? This is the important part of the presentation, where I show you an example of what you can do in PHP to support server push. So let's walk through a few examples. So this is Firefox. In this example, it's really easy to tell if you're serving requests over HTTP2 using Firefox's Web Developer Network Inspector. So if we take a look at the Network Inspector, we'll see that Firefox shows us the version of HTTP, and it will also include this header, xFirefox Speedy, with a value of H2. H2 means HTTP2. Now let's compare this to the same request in HTTP 1.1. Nothing special about this. This looks pretty normal. This request that I'm demonstrating only has a few objects that it's loading, but if you can imagine this having a lot of different images, this would go on and have tons of different images and make the request much larger. But in this one alone, it's 490 kilobytes. That's actually pretty big, but that's because it's got Bootstrap and jQuery that's being loaded in. Now this is HTTP2 without server push. You can see that the network requests look very similar. They're loading each one individually, and it shows you the milliseconds. This is with server push, which looks a little odd here, because you see this one request, which takes all the time, and then the other ones below it really don't show much at all. This is because we're using server push. We can verify that with a tool called ng-HTTP from the command line. And this is hard to see up here, but there's some important things to point out here. You can see the frames. You can see each frame and some of the flags on that frame. I have the data turned off here, but you could also turn on the data to see the data. You can see the headers down below. You can see the method is get, the path, the scheme, the authority, some of our accept headers. More of the output shows us what's going on. These are push promises. In this, ng-HTTP has not made request for these assets yet. These are files that have been pushed to ng-HTTP from the server. And you can see that there's bootstrap.css, bootstrap.js, and theme.css in this slide. Now, how does that work? It's actually really easy. We use the link header. Now, the link header comes back to the client, and you would think that that tells the client something about it. But it also tells the server some information. Using the preload link relationship, we're able to tell the server to go ahead and send these files before the client requests them. It's still in draft form, but it's gaining adoption. And it provides support for HTTP2 server push through the link header. And it's defined here. So you can download these slides and go read along with that later. Here's what it looks like. Very simple. We have a link header. We define the path to our resource, which, by the way, has to be in the same domain. It can't be cross-domain. We define our relationship, which is preload. And then there's this as attribute. And the as attribute defines how the client should interpret that, in this case, style. And in PHP, we can use the header function, passing false as the second parameter, because that false tells PHP not to override previously set link headers. But your framework of choice has an ability to set a header, and you should use that, as long as you tell it not to override previously set link headers. And so this is really all there is to it. And you can use some of the server superglobal variables to determine which version of HTTP you're running. And as a result, you can say, if I'm running HTTP2, go ahead and send all these links. So now you have server push. Now, I hope that through this presentation, I've taken more time than I should, so I apologize. But there are drinks afterwards outside, so everyone will be happy. But I hope that you've got an idea of what HTTP2 was created for, why we created it, or why the internet community created it, and what it can do for you, and what you can do right now. So thank you very much. Long live HTTP2. And are there any questions?
Thanks so much, Ben.
Thank you.